As we have seen, the BB84 protocol, it exploits the superposition property of quantum mechanics. Superposition property and also the uncertainty in measurement. You know, if you use different bases, different orthonormal bases, you always have uncertainty in measuring the state of the qubit. So these properties were exploited. Now, this the other protocol that I'll discuss, it was first published by Ekert in 1991, exploits the entanglement property of quantum states. And it uses the Bell inequality test to verify that there has been no eavesdropping. And it works like this. Again, we have Charlie, you know, C. Charlie prepares an entangled pair of qubits. As I mentioned, how we implement these things, how we can produce entangled pair of qubits, and how we can do all these kind of measurements and protocols. We'll discuss them next semester. This semester, we are just discussing, you know, the protocols themselves, you know, how the protocols work. Protocols and how we analyze these protocols. This time, let's suppose Charlie prepares the state cat psi minus, which is 1 over square root of 2, cat horizontal vertical minus cat vertical horizontal. Now again, I'm assuming over here we are using photons, but you can always use the standard basis, cat 0 and cat 1, instead of the horizontal and vertical polarizations. As I said, these names, you know, in this bra and cat notation, they are just labels. You know, they can be interpreted in any way you want, as long as we are talking about distinguishable, you know, basis quantum states. Now, Charlie prepares this state, and one of the qubits is sent to Alice, and the second qubit is sent to Bob. According to this EPR pair is produced, and one qubit goes to Alice, and another qubit goes to Bob. Now, Alice and Bob again generates this time random numbers, 3 random numbers. They make randomly, you know, again uniformly distributed randomly. They measure their qubits either with phi a minus with a 0 angle, or phi a2 with a pi over 4 angle, and phi a3 which is the pi over 8 angle. So randomly, at random, Alice measures the qubit that she receives, right, at these angles, 0, pi over 4, and or pi over 8. Similarly, Bob also at random, you know, uniformly distributed, this time measures at these 3 angles, pi over 8, 3 pi over 8, or 0. So at random. Now, for the cases phi a1 equals 0 and phi b3 equals 0, and also phi a3 equals pi over 8, phi b1 equals pi over 8, there is a complete anti-correlation, right? I mean, if these angles are the same, is 0, 0, phi a1 is 0, phi b3 is 0, or similarly pi over 8, yeah, right? Phi a3 equals pi over 8, or phi b1 equals pi over 8. So if Alice and Bob happen to measure their qubits these angles, that means there is complete anti-correlation, right? In other words, if Alice is measuring horizontal polarization, Bob simultaneously is measuring vertical polarization, and vice versa. If Alice is measuring vertical polarization, Bob is simultaneously measuring horizontal polarization. There is complete anti-correlation, and these can be used as symmetric keys. So Alice and Bob, when they also publicly announce, the angles that they use, they make a measurement at random, but they also at the same time they announce. So if it happens that phi I equals uh, phi A equals 0, phi B equals 0, or phi A equals pi over 8 and phi B equals pi over 8, since these measurement angles are announced publicly, they can use, and there is complete anti-correlation according to the Bell state. So these can be used as symmetric keys. And the other two, the other measurements, if it turns out that Alice and Bob, they measured in these other angles, then they use this as a proof, that there has not been any eavesdropping, and they use the CHSH or Bell inequalities that we just discussed on these other random measurement pairs to validate, that there is still entanglement between the qubits. In other words, there has not been any interception, because as soon as there's an interception by an eavesdropper, by Eve, right, the entanglement is dropped, and we have a classical situation. So classically, the maximum success rate we discussed was 0.75. But now, using the results of the other measurements, right, we can compute this Bell inequality or CHSH inequality that we discussed. If it turns out to be over 0.75 or maybe maximally 0.85, then that means the entanglement has been preserved, and there has not been any interception by an eavesdropper. So the keys that are obtained using these other measurements, 0, 0, and pi over 8 and pi over 8, they can be securely used as a symmetric key by Alice and Bob. Okay. So this we could do the analysis. I have done the analysis of this protocol in the class last semester. I could also do the analysis, but also I could assign this as an homework. But this particular protocol is also an important key distribution protocol. And this is the importance of this over the BB84 protocol is this is a device independent quantum key distribution protocol. In other words, the security of this protocol does not depend on the quality of or the security of the device that is producing these keys, these random numbers, because the way we are proving, randomness is through the CHSH, inequalities. It's not dependent on the characteristics or security, of the devices that are producing these random numbers. So they, as such, they constitute an important class of quantum key distribution protocols, which is device independent. So the security of this protocol does not depend on the particular equipment, but that only depends on the random choice, of phi sub A and phi sub B, the choice of the measurement angles that Alice and Bob uses. Are there any questions on the quantum key distribution, Ekert protocol in particular?
I want to ask you